Hello everyone, and welcome to the course ENCH3RT Reactor Technology Fundamentals. I think it's one of the most interesting topics in the whole of chemical engineering, and some of the principles that you learn here are applicable in many other areas that involve developing a model of a system and predicting how it's going to perform over time. So that's reactor technology fundamentals, and let's let the material speak for itself. Looking at the study hours required, it's a 16 credit course, so that translates to 160 hours. There's a suggested breakdown here about lectures and tutorials versus self-directed learning. So you can read the details here, but rest assured that you do need to put a lot of time into learning the material and into really just thinking about the material and what it means. So that's very important to do in reactor technology fundamentals in all courses, but especially in this course where there are some new concepts and it takes some time for them to grow on you. So, of course, the prerequisites, we assume you've covered all this. And then I'm the module coordinator, and of course you have my email address by now. Prof. Lockhart is the other lecturer on the course, and you'll meet him in the second part later in the year. Of course, the venue is listed here, but this semester we won't be using that. Remote teaching and COVID-19 and all that. All right, here are the outcomes. So if you complete the course successfully, you'll be able to understand and calculate reaction rates, the yield and composition coming out of the reactor. You'll be able to create mass and energy balances on the ideal reactor types, namely the perfectly mixed reactors, the plug flow reactor, the batch reactor. So you'll be able to do the mass and energy balances on those. But then we will also look into non-ideal types of reactors where the flow patterns are not so well defined. You'll still be able to do those balances on those non-ideal reactors, and even in the face of complex catalytic influence. So even when you have particles with catalysts embedded in them, that's going to influence the reaction rate. We'll still be able to design our reactor. In terms of your Engineering Council of South Africa, the accrediting body in terms of their defined knowledge areas and outcomes, this course contributes mainly toward the engineering sciences area. There is a bit on the coding and simulation side as well, because we use Python or MATLAB or one of these languages to do some of the computational work. In terms of, we can take a detailed look at some of what we'll be covering. So in my part of the course, we'll be starting with the basics of reactions. So the basic concept of stoichiometry or reaction kinetics and thermodynamics. So there's some overlap with your chemistry courses here. And then we'll move on to creating the mass and energy balances for the ideal reactor types, and then starting to account for the influence of non-isothermal behavior. So isothermal behavior, we'll be dealing with simple reactions and ideal reactor types to begin with. Then we progressively start relaxing the assumptions and then dealing with non-ideal systems. And we'll be looking at nonlinear dynamics and chaos theory like analysis a bit later. And then we'll also deal with the non-ideal flow types. So we've mentioned the ideal flow types, perfect mixing, plug flow, batch, but we will look later at how we can combine those ideal types and be able to model even non-ideal flow type reactors. So the concept of residence time distribution is extremely valuable there. Later in the course with Prof. Lockhart, you'll be looking at analyzing data that you may collect from lab type reactor. So analyzing that data and then converting that data into parameters for your reaction kinetics. You'll be looking at the case where you have many reactions that are competing for the reactants, and looking at how to design your reactor in the face of that. You'll also look at gas-solid types of reactors, And the interesting bit here is that your reaction surface area is changing with time. And so that complicates our efforts to predict the reaction rate in the reactor. But we'll see, we have nice, clever ways of dealing with that anyway. In terms of your catalytic reactions, with catalysts, several complications can arise. So, for example, the surface area of the catalyst may be changing with time. You may have an influence of a deactivating catalyst. Then the kinetics themselves become affected by adsorption and desorption rates and so on. So there are some nice, interesting complications. But through it all, we are able to still come back to a nice, well-defined material balance and still predict the reaction rate and hence design the reactor. So there's some very interesting theory in this course, and you can look forward to that. Here's how we assess the course during these remote teaching days. Basically 4 tests, 25% each, and in those tests we'll have a combination of understanding type questions, so multiple choice questions and other types that probe the theoretical understanding. And then that's coupled with applied type questions where you're actually solving problems and designing reactors, predicting the volume needed or the flow rates across that reactor. So you have these different types of questions that will be covered across all these assessments. We'll be announcing the dates of those assessments later in the semester. We typically go through this exercise where we try to balance all the number of tests and assignments across the semester. The usual policy applies if you miss an assessment. So if you have the evidence for missing an assessment, and if it's a reasonable reason, then we will grant you access to the make-up test. In terms of the textbooks, these are all very good books. So Fogler, of course, the mainstay in a way of chemical reaction engineering. And then Levenspiel is another good book. They do a fair bit more in terms of the particles and the residence time distribution in Levenspiel. In Holland and Anthony, there are some very good sections on reaction kinetics in particular. Polymer reaction engineering is nicely developed in this book as well. So these are all very good books. So that's pretty much it in terms of introducing the course, and maybe to introduce myself. Yes, I've spent about 20 years in reaction engineering. I've since moved on to the area of artificial intelligence and data science and machine learning and that kind of stuff. But reaction engineering, it's always a great pleasure to work with, and I still maintain projects and research topics in this area. Prof. Lockhart also works in reaction engineering, and he's done some great work, especially on the experimental side. So with that, we'll be releasing lecture content regularly each week, and we'll have a Zoom session where we can have our discussions. That's about it. If there are any more questions on the logistics and the setup of the course, please feel free to contact me.